Okay. All right. So I'm going to give a talk about some electronics calculations that they're pretty basic calculations, but they're ones I realized I didn't understand when I started working with Pis and plugging stuff onto GPIO pins. So for context, my background is I'm a computer programmer and a mathematician at heart. I'm not really a hardware electronics person. And this is just something that hold on. My mum is calling me on Facebook. Hold on.
Classic.
It's ringing in my ear, so I have to turn it off, else I'm not going to be able to talk at the same time. Sorry about that. Hold on. There we go. Okay, share screen. Okay, can you see that?
Yeah, I can see that.
Yeah, okay. So the electronic stuff I just came into as I started playing with Pis, just sort of sticking stuff on for fun rather than as a job, which the programming and the maths is for me. So I'm going to talk about what happens if you have probably your simplest GPIO pin project that you can do on a Pi, which is you stick an LED onto a GPIO pin and you make the Pi flash the light on and off. It's a pretty common tutorial. You'll see it for Raspberry Pis, you'll see it for Arduinos, pretty much anything programmable with the output pin. You'll see a tutorial for it somewhere on the internet. So I Googled one, there's a link there. If you click on the slides, you can look at it. And that tutorial has this picture, which is a Raspberry Pi at the bottom, an old one with a little stumpy GPIO connector. And then it's got an LED and a 330 ohm resistor. And I found myself wondering, what is that 330 ohm resistor? Why is it 330 ohms? And what does that really mean? Because you buy a pack of resistors, there'll be 22 kilo ohm resistors, there'll be 10 ohm resistors. Why does it have to be 330 ohms? So if you dig in a bit more, you'll come to pages which web pages which will give you calculators, and you'll get given this formula that looks like this. And it's like, well, the way you calculate what the resistance is you take the supply voltage and you subtract off the LED forward voltage and you divide it by the LED desired current and you get given the resistance. And it's like, all right, fine. But that's just this kind of opaque formula that didn't really mean anything to me, even though when I plugged the values in, it all worked. So I sort of dug into where does this formula come from? And that's very much what I'm going to talk about today. Okay, so I'm going to forget about the GPIO pin for now completely. I'm just going to say, if we have a power supply on this diagram, it's a 5-volt power supply, and there's our resistor, and there's an LED. So if you can see my video, I'm not sure you can. It's an LED from this little bag of LEDs I got from Protopic from Spark Fun. And that's, so it has some specifications. It says 2 volts, 20 milliamps. And the calculator says I need to use 150 ohm resistor. So okay, wire that all up and the LED will light up nicely. So what's going on there? So I'm going to talk a little bit about what electricity is first. So electronics is when you've got things like electrons flowing around a circuit. So I say things like electrons because if you have electricity flowing through other things that aren't wires, you have other particles that act kind of like electrons. So if you put electricity through salty water, through brine, there'll be salt ions. instead of electrons. And so there's all kinds of things. But the standard thing is you talk about an electron worth of electrical charge flowing around a circuit. And an electron's pretty tiny. So there's a more convenient unit that people talk about, which is called a coulomb. And you won't see that used very much, but it underlies a lot of what's going on. So that is 6 million electrons is what a coulomb is. So if you think about how, you know that water is H2O molecules, but it's much easier to talk about a pint of water rather than 6 bazillion molecules of water. So that's what a coulomb is. It's like a scale, a scaled up version of an electron. And we don't really talk about that much. What we actually talk about is electrons moving around a circuit, and that's an amp. Okay, so if you have 1 coulomb of charge, electrons or whatever, moving through your circuit, that's called 1 amp. Okay, so if you imagine 6 million electrons flowing around out of your power supply, that power supply is supplying an amp worth of current. And we've got standard scientific units. You can have a milliamp, and a microamp will be the other one that you might encounter as well. And we normally use the symbol I to represent current when we're talking in formulas. So you might say I equals 20 milliamps if we're talking about LEDs. So in terms of LEDs in this circuit, this LED here is specified to have a maximum current of 20 milliamps. So that means if I let 20 milliamps of current flow through this somehow, it will glow just right. If I don't have that much flowing through it, it'll be a lot dimmer. If I put more than that in it, it'll be brighter for a bit and then probably explode or something like that. Okay, so that's what I want to do to make my LED light up, is put 20 milliamps of electrons through my circuit. Okay, so there's a law called Kirchhoffs Current Law, which basically says your electrons flow round, or your current flows round. They can't just magically appear or disappear. So if I've got a component and 1 milliamp is going in, then 1 milliamp must be coming out somewhere else in that component. Okay, the rule doesn't say what's happening. So if I've got lots of pins, it doesn't say how that current will be distributed between the lots of pins. But if it's a simple thing like an LED or a resistor, if 1 milliamp is going in one end, 1 milliamp must be coming out the other end. If I've got a piece of wire and 1 milliamp is going in one end, I've got to have 1 milliamp coming out the other end. And that's like if you put water in a pipe, the water that goes in one end also comes out the other end. So what that looks like on this LED circuit, if I've set it up so that I know 20 milliamps is going across the LED, that means everywhere else around this circuit, there must also be 20 milliamps flowing. So specifically, there must be 20 milliamps flowing across this resistor. There's got to be 20 milliamps coming out of the power supply and going around, and there must be 20 milliamps coming into the bottom again. And we're going to use that rule to do some calculations later on. There's a bit more of a complicated setup here. I've copied the LED and the resistor circuit twice. So I've got 20 milliamps flowing through this LED, which means there must be 20 milliamps going through this resistor, and the same thing over here. But if you look at this junction, there's 20 milliamps coming this way and 20 milliamps coming this way, which means there must be 40 milliamps coming in from the power supply. And that's should be pretty straightforward. I've got two things each drawing 20 milliamps. I need to supply 40 milliamps. It's not rocket science, but I just want to be clear that that is the rule for how current works. And then the other thing we talk about lots is voltage, which is measured in volts. And that is basically when you have your charge or electrons or whatever, as they flow across a voltage difference, across potential difference, they can take in or they can release some energy. So if 1 coulomb of charge moves across 1 volt, it gives out or takes in 1 joule of energy. And if you do that over time, then 1 amp of current across 1 volt gives 1 watt of power. So you can think about voltage a bit like height. If I drop a cup off my table, it might bounce. If I drop my cup off the top of a very high cliff, it can be the same cup, the same electrons, but it's gone through a much bigger height change. And by the time it reaches the ground, it's going to have collected a lot more energy from gravity. And Kirchhoff has a voltage law for that as well. And that says the voltage has to add up to 0 as you go round. So the power supply, if we start at 0 at the bottom, the power supply adds on 5 volts, which means that between them, we've got to drop 5 volts between the LED and the resistor. The rule doesn't say how that voltage is split up between those 2 components. It just says whatever the voltage is for the resistor and whatever the voltage is for the LED, if we add them up, they have to be 5 volts because the power supply is also 5 volts. Okay, so there's some other rules. One of the rules for LEDs is that when an LED is glowing, it has a forward voltage. And for these LEDs I got from SparkFun, it says the forward voltage is 2 volts. So what that looks like here is I know there's 2 volts here. And I know how I have to drop 5 volts in total, which means the resistor must be taking up the other 3 volts. Okay, that's a pretty simple sum. I know 5, I know 2, 5 minus 2 equals 3. And I'm going to use the fact that I know that the voltage across the resistor is 3 volts in a calculation in a bit too. So what I could do instead is put 2 LEDs in and a resistor, and I would need a 50 ohm resistor in this case, not a 150 ohm resistor. And the voltage distribution, it's still between the 3 of them, they've got to be 5 volts, 2 volts for one LED, 2 volts for the other LED. And so this resistor is just going to have 1 volt across it. So it's going to behave differently than the 1 LED case. And if I put them in parallel, that diagram again, this is 5 volts. I've got to drop 5 volts across the resistor here and the LED, and the same here. So we're going to end up with 3 volts across these resistors, because you can look at each parallel branch separately. Oh, sorry. Each parallel branch has to drop off 5 volts each. So there's current measured in amps, there's volts, voltage measured in, or potential difference measured in volts. Those are the sort of 2 main concepts that we need. We've got some rules on how they relate to each other between different components. So now I'm going to talk about our 2 components. We've got the LED, a light emitting diode, and that will come with a specification like 20 milliamps, 2 volts. And what that means is if you put a voltage across it, it won't let any current flow at all until you hit 2 volts. When you hit 2 volts, it will suddenly let as much current flow as possible through it. But if more than 20 milliamps flow through it, it'll explode or it'll break. It'll probably just flash and stop working. Okay, so if I just take a 5 volt power supply and an LED, the LED will let as much current flow through it as the power supply can supply. So it'll be something quite like a short circuit until it breaks, which it isn't what we want to do. And so I need to do something to limit the current to be 20 milliamps. Okay. The other component is the resistor, and that's the thing that is going to let us do that, that current limiting. And so the way you describe a resistor is in its resistance, which will be like 150 ohms, for example. And what that means is that if you have a voltage across a conductor like a resistor, the amount of current that it lets flow through it is in a constant ratio. So if I double the voltage, then it will double the amount of current. If I halve the voltage, it will halve the amount of current. And so that ratio is called the resistance. So 150 ohm resistor means if I put 150 volts across it, I will get 1 amp current flow. I think I have that the right way around. Yeah, okay. And if I had a 22 kilo ohm resistor, I would have to put 22 kilovolts across it to get a 1 amp current flow. Or if I just put a smaller voltage, I'm going to get a proportionally smaller current flow. Okay. So that relationship, which is the voltage is equal to the current flow times the resistance, or equivalently, the resistance is the voltage divided by the current. That relates the voltage and the current through this ratio, which is called the resistance. And that doesn't apply to all components that you use. It only applies to things that are basically conductors. So resistors, it will apply to wires. I think Andrew did a talk once on the resistance of USB power supply cables, for example. So anything that looks like a wire basically follows this law. But things like the LED don't follow this law. They let no current flow, and then suddenly they let lots of current flow through. So they behave differently. So how do I put these together to make the LED have exactly 20 milliamps flowing through it? Well, I've got 2 volts here. I've got 5 volts to drop across the whole circuit, which means I've got to drop 3 volts across this resistor, or I'm going to drop 3 volts across this resistor. And so I want to say, what resistance do I pick to get the right current through this resistor? How do I know what the right current is? Well, I know I want 20 milliamps here, which means I know it has to be 20 milliamps everywhere. So what resistance do I pick so that if I put 3 volts across it, it will let 20 milliamps flow? Okay. And so your calculation there is 5 volts minus the 2 volts for the LED means there'll be 3 volts over the resistor. And so then the resistance is the voltage divided by the current. So 3 divided by 0.020, that's 20 milliamps. And that result is 150 ohms. So that little calculation down here at the bottom is this calculation that I showed at the start. We've got our supply voltage minus the LED voltage. So what this really means is the voltage that's left over to be across the resistor divided by the current that I want through the LED. And that happens because the current through the LED is also the current through the resistor because of the current law. So those are 3 laws that you can stick together and come up with reasoning about that. So there's a few other things you can do that are sort of related to this. So here's a thing. I showed this diagram with 2 LEDs in it, and the LEDs have both got 20 milliamps flowing through them. So they'll both glow at full brightness. Excuse me. So somehow through this circuit, I'm going to get twice as much light out than if I just use 1 LED. But the power supply is still just supplying 5 volts, 20 milliamps. So what's happening? Why where am I getting this second LED worth of power from? And what's happening here is this resistor, in this case, only has 1 volt across it. So earlier on I said voltage is when current flows, how much power, how much energy and power is released. So a resistor will release that heat as will release that power as heat. So this little resistor will get a little bit warm, and the resistor in the 1 LED circuit has a bigger voltage across it and the same current. So this resistor will be in the 1 LED circuit will get hotter. Okay, so this is a more efficient circuit because we're generating less heat and generating more light. In the other circuit, we're going to generate 3 times as much heat in the resistor. So what we'll end up with is a brighter but cooler light. So it'll be a little bit like the trade-off with an energy efficient light bulb. It gets less hot and it's brighter. Here's another thing you can use those rules for. So if I've got 2 resistors, turns out they behave as if they were 1 resistor, and that's one of the rules you'll learn if you do electronics at high school, is how you work out what they're the equivalent resistor to, and you can derive that from these same laws. So we've got a current that flows across, and the current that flows through this resistor has to be the same as this current because of the current law. We also know from Ohm's law how the resistance and the voltage are related to each other. So we could say that the voltage across resistor 1 is the current times the first resistance, and the voltage across resistor 2 is the same current times that resistance. But we also know whatever voltage we've put across here, it has to be shared out somehow between the 2 resistors. So the sum of the voltage here has to be the sum of the voltage here. And if you put the formulas together and do a little bit of rearranging, what you end up with is that the equivalent resistance is the sum of these 2 resistors. Okay, so this circuit is the same as 150 ohm resistor. And that's not a particularly crazy result. If you've done any electronics at all, you know that you can just stick resistors in series and you just add up their resistance, and that gives you the equivalent resistance. But it is derived from putting together the 3 of the current law, Ohm's law, and the voltage law. And if you know those, then you can work out this without needing to know that rule. And you can do the same kind of calculations if you put resistors in parallel or if you combine them in other ways. You basically figure out all the equations from these laws and simplify them in the way you want to get the result you want. Okay. And I think the last interesting thing is you can start building things like constant voltage sources. So we know there's 5 volts dropped across here, 2 volts across the LED. So if this is 0 volts, this will be 2 volts, and then 3 more volts goes across the resistor. If I increase the power supply a little bit to 6 volts, this will still be 2 volts across here, and there'll be a bigger voltage drop across the resistor. Or if I reduce the power supply, the voltage drop across the resistor will go down, and the LED is still going to be going to make 2 volts appear here. So if I stick a little connector on here between the 2, whatever the power supply voltage is within limits, I'm always going to get a 2 volt power supply out here. And you don't have to use an LED here. I used an LED because I've talked about this circuit before. But if you were going to do this for constant voltage circuits, you can get much more appropriate diodes that don't glow and have much better tolerances. for doing things. You could get one that will help you regulate to 3.3 volts or 5 volts or other common voltages. Okay. And the last thing is, if I really did attach this to a GPIO pin rather than just a plain power supply, what would happen? So on a Pi, that would probably be 3.3 volts when the pin was on. So I'd need to recalculate this resistor. But all the rules I've talked about would apply as before when the pin is supplying 5 volts. What happens when the GPIO pin is set to 0 volts? Do those rules still apply? It turns out they do. So there will be a 0 volt potential difference between ground and the IO pin, which means there's got to be 0 volts across here. So the sum of the resistor voltage and the LED voltage has to be 0. Okay. Well, that means the LED is not going to have any current flowing because it's below 2 volts. And the resistor is going to have 0 volts across it. And by Ohm's law, that means it's going to have 0 amps flowing through it. So that works too. There's 0 milliamps flowing around, 0 milliamps through here. That has to match up with 0 milliamps flowing through here, which also works. So those rules also kind of trivially hold even when the system is turned off. Okay, so the summary of that, we've got current, we've got voltage. There's ways in which some facts that are true for circuits as a whole. So we've got the current law that says you can't have current disappearing or reappearing, but you can distribute it. You've got the voltage law, which says that you've got to drop your whole supply voltage across your components, but it doesn't say how that's distributed. For conductors, so resistors and wires, we've got Ohm's law, which relates how the voltage and the current work. For things like diodes, LEDs, there's different behavior. That's what makes them interesting components, that they don't behave like resistors. And just with that very small set of rules, you can derive quite a lot of stuff. Lots of things that you learn as laws, like adding resistors together, that they flow from these facts without needing to be fundamental laws themselves. And that's the end. So I will stop my screen share. Don't know if anyone has any questions there. Oh, chat.
Well, thanks for the thanks, Ben.
Yeah. Hold on.
Background electronics.
Okay, let me just go through the questions. Okay, hold on, because I just brought up the chat window. Okay, so are we using the same amount of available current when we introduce a resistor? How do you reduce current without wasting energy? Yeah, so someone said use a lower voltage battery. Yeah. There are other interesting components that you can do. You can use things like capacitors and inductors and do other stuff which doesn't follow these rules. So they have their own set of rules. Yeah, someone says we could have a long enough copper trace to replace a resistor. Yep, you can. The wires are like small resistors. Yep. Yeah. So one of the things I've done, that skull that's behind me that's glowing red, I'm not sure if you can see how there. That is originally the electronic side of that was I wanted to make a fixed current source so that whatever power supply you connect to it within a range, it will always let 20 milliamps flow through the LEDs. And that's built with a couple of transistors arranged in a feedback loop. So originally I was going to talk about that, and then I decided I was going to talk about these rules instead. Yeah. Okay. Any other questions?
Yeah, I think there's one other point of using the resistor, and that's to protect your GPIO, because I think it's limited to something like 7 milliamps on any one
Yeah.
pin,
Yeah.
and 20 milliamps total. So
yeah. So
that's
the specs I looked at recently were 16 milliamps per pin and 50 milliamps total. But that was just like Google, what are the specs? So I don't actually know.
yeah, it's
You have
better
you
to
might,
err on the side of safety.
Yeah. So those are actually, if you've got a 20 milliamp, either of those specs, if you've got a 20 milliamp LED, that's neither of those specs that either you or I talked about would be enough to drive one of these LEDs at full capacity off one pin, and you'd only be able to run two even if you did something fancy. So the sort of next stage of circuit to look at is transistors, and they act like little current amplifiers. You feed in a little bit of current down one pin and it lets a lot more current flow down another pin. So you'd be able to use your GPIO to supply a little bit of current.
Well, I just run my GPIO into a relay and then have a separate power supply for through the relay, and then I can put a lot more current through that way. Yeah,
as long as your relay is taking less than whatever you choose your limit to be, like 16 or something milliamps.
You can get relay modules that use microamps.
Yeah, they use very little. It's amazing.
And then you control motors, whatever you like.
Yeah,
I run 7
more quickly.
Yeah, I've got 7 LEDs that I run quite happily with the GPIO, so it doesn't complain or blown up yet.
Yeah, no, the stuff that I run in practice off IO pins is way over spec. Like I quite happily stick LEDs and pins and do all kinds of stuff.
But your one diagram, you had 2 LEDs in series.
Yes.
And they say basically if you have in a few websites say you should have 1 resistor per LED, but I've got my house number in LEDs. I did a little presentation a while ago, if you remember. I've actually just got 1 resistor.
Are you talking about this diagram or this diagram?
No. So the next one.
The parallel
but that
LEDs.
instead of the 2 resistors at the top, you actually just have 1 resistor on kind of below where the 40 ohm is.
Yeah. I do that as well.
They say that's bad practice, but it's like it's working absolutely fine. They should say you should have 1 resistor per LED.
Yeah, so I think the problem happens there is, which I've seen talked about, but I also
if the LEDs are
slightly
different rated, then you have a problem.
Yes,
because
if they have different voltages, then theoretically this doesn't work.
Yes, if you have like a blue and a red one, only one of them will work. But if they're all exactly the same spec, it does actually. Where if you have 1 resistor, it's okay.
In practice, it's been working fine for me as well. But so what would happen if these had slightly different voltages? Is with separate resistors, you get a slightly different voltage drop across here.
Yeah,
and that makes it work. But I've got my other LED project that I have just has like 4 or 5 LEDs wired up through 1 resistor, and it works fine.
Yeah, then I do that off my relay, and then at least I keep the power. I don't. When you're running like 30, 40 LEDs, you can't do that off GPIO, of course.
Yeah.
I did have a question about PWM. I don't know, Ben, if you know, if someone else does, but I don't know how to theoretically calculate how much the brightness I'll get out of a given PWM signal. I'm not quite sure how PWM works. I know it works, but I don't know how it works.
Oh, so it's the amount of current flow is basically a percentage. So a PWM number is a percentage or a fraction. So you can have 100%, which is your pin is on, or you can have 50%, your pin is on 50% of the time and 50% off, or you can have 0% and your pin is not on at all.
Yeah, I know, but there's
and that's the fraction
involved, so it doesn't react instantly. So by the time your signal's going back to 0,
you're
gonna get some weird.
The other really non-linear thing with LEDs when humans are looking at them is if you halve the current flow, it doesn't appear half as bright. So it will appear almost full brightness if you halve the current flow. And you see that on things like neopixels. If you set a neopixel to full on or you set it to half on, it looks almost the same compared to if you set it to a quarter on. So there's a thing called gamma correction, I think, which you'll see people who are doing RGB LEDs who care about getting the color mix right. There'll be lots of talk about that, and it's just this weird curve where the current flow or the PWM percentage for your LED doesn't reflect what a human sees. Yeah, and for me, I've started experimenting with that in the last 6 months or a year maybe, and doing those calculations or using libraries to do it. It's not hard. That has massively improved the quality of my LED projects.
Yeah, a lot of libraries just feed those in. Feed that at the beginning of when you first initialize the library.
Yeah.
Any other questions?
Ben, I had a question.
Yeah.
Sort of, I was always under the understanding. I wrote a comment. The understanding that in the forward direction, a diode has negligible resistance. It's just so therefore it's effectively a straight line, and it's got infinite resistance, or effectively infinite resistance in the reverse direction. That's effectively the point of a diode.
Yes. Yeah.
So in a circuit where you've got two diodes in series with a 50 ohm resistor, which I think you showed on your diagram, effectively you'll have 100 milliamps flowing.
No, because the LED, so the LED doesn't have a concept of resistance, because resistance is this thing that is a property that resistors have. So you feed in, you put a voltage across it and a certain current flows in a particular ratio, which is what the resistance is. LEDs don't have resistance in that sense. So they will. So
effectively, it's the same as bypassing it. Effectively, so it's effectively a line going through it.
It will still drop 2 volts across it. So if you get a multimeter out and you stick it at different points.
How can it drop 2 volts across it if it doesn't have resistance?
Because it's not a resistive load.
It has to do with quantum tunneling, but I think that's maybe.
Yeah, I mean, there's like there's physics involved. The answer is that you have this gut feeling that it should obey Ohm's law, right? And that's wrong. It's the wrong gut feeling. Okay.
It's not a constant resistor.
Yeah. So there's this
resistance
rule.
changes depending on current.
Yeah. This is the
intuition. Okay. So it does have a resistance, but it's variable depending on the current.
Well, the resistance
on the voltage. And the voltage,
yeah.
Yeah. So the resistance in the sense of Ohm's law is if you draw a graph of you put a voltage across it and you draw a current, that will be an absolute straight line if it perfectly follows Ohm's law, right? And the slope of that line is the resistance, as in the ohms. So it will be 150 ohms is the slope here, or 50 ohms is the slope like this or like that, right? So whatever voltage you put in, it will multiply it up by a constant and give you a straight line. If you draw that graph for an LED, it won't look at all like a straight line. It will be 0 and then suddenly infinity or very high. So this sort of dogleg curve. So there isn't this concept of saying, here's this dogleg curve. What's the slope of this dogleg curve? It doesn't have a slope. There is a current. There's a particular current that will flow defined for every voltage that you put across, but it isn't in this constant ratio.
Okay. Thanks very much.
Cool.